Okay, our next session is Mustafa Abduljabbar, optimized all-to-all connection establishment for high-performance MPI libraries over InfiniBand. Mustafa is a research scientist at the Network-Based Computing Lab at Ohio State University, currently involved in several MPABH2 research projects to provide highly optimized support for Rocky V1 and V2 Broadcom adapters. Mustafa?
Thank you for the introduction, Phil. Can you see my screen?
Yes,
in full screen mode,
perfect.
presentation mode. Okay,
Absolutely.
Thanks a lot. Okay, so yeah, I'll be presenting on behalf of Shulay and DK Panda from the Now Lab group at the Ohio State University. And I'll be talking about a scheme for optimizing the all-to-all connection establishment for MPI libraries running on InfiniBand. So as an outline for my talk, I will be starting by giving an introduction and the background information necessary to motivate the work, and I will highlight the challenges in general, and I will talk about the design optimization and share some performance evaluation results of our design scheme, and then I'll conclude my talk. So if we look at the current trend of HPC clusters architectures, and given the saturation of Moore's law and the sunset of Dennard scaling, we will see an abundance of multi-core and many-core processors technologies. Those are communicating over high-performance interconnects, such as InfiniBand, with very low latency, even lower than 1 microsecond, and also with very high bandwidth, reaching up to 400 gigabits per second. And those nodes host accelerators, very fast GPUs from multiple architectures, as well as fast storage. So the key point here is that conventional communication such as Summit or Sierra, for example. Both of these feature IBM Power 9 architecture processors. And in terms of the number of cores, we're looking at 44 cores supporting hardware multi-threading. So that number is multiplied by 4 when hardware threading is enabled. So we're looking at roughly over 170 hardware threads that can potentially inject traffic into the network. So before I move on to more technical details, this is the project that we're working on. It's the MPABH project where the designs take place. So MPABH is an implementation of the MPI standard. It's a well-known implementation that features high-performance interconnects such as InfiniBand, Rocky, OmniPath, Rockport, Slingshot 10 and 11, and even it covers cloud providers such as AWS, EFA. It has been used even on top 500 and top 100 supercomputers, as we give some examples here. It has several releases supporting GPUs, advanced interconnects, and so on. And it has over 1.77 million downloads from the OSU website directly. So going on to the recent trends and back to our motivations. As I said, the motivation of this work is sparked by the recent trends of contemporary high-performance computing clusters, where we know that there is an increasing number of cores. For example, we have over 100 cores per node in the AMD EPYC and the Intel Sapphire Rapids platforms. And in conjunction to the increase in the number of cores per node, we see also a trending decrease of the number of nodes in a given HPC system. So, for example, in the past, we spread 8K cores over 512 nodes, each featuring 16 cores per node. However, nowadays we can have this many cores over just a handful of nodes compared to the past trends. So this makes it even more challenging for designing MPI libraries for that establish connections for all of these communicating cores, even on a smaller number of nodes. So the focus of the work is to minimize the connection establishment for job startup in general. And I found it necessary to give some quick background information. I know that I'm speaking to a very experienced audience here, but just as a refresher, QPs are building blocks for RDMA communication. So before any send and receive operation takes place, there has to be exchange of these QPs and some connection establishment. So the first step would be to exchange the QP information, exchanging IDs of the networks, such as the LID and GID, and the QP identifiers. And I think most of the optimizations go to this particular phase of the connection establishment that we're proposing in this work. And then the QPs will be modified to, the state of the QPs is modified to an RTL request ready to receive, and then it's modified to ready to send so that the fully bidirectional communication is supported. As I noted before, these optimizations are incorporated in MPI libraries. So I assume that we know that MPI is a popular programming model for parallel HPC applications to support distributed scale-out communication. And for MPI, there are two major yet intuitive connection establishment schemes for RDMA communication. These are the all-to-all connection establishment and the on-demand connection establishment. So if we look at these two figures we're sharing here, and if we imagine that we would like to, let's say, carry out a broadcast operation. So maybe it's more intuitive to look at the on-demand connection establishment. So for a broadcast to take place, if we think about a leader-based kind of algorithm to implement broadcast, all you need to communicate during the broadcast operation would be the QPs of the leader nodes here. So during execution, if we look at the direct information, the node that is broadcasting the data marked by node 0 in here would be getting the QP information from all the leader nodes of the remaining nodes. And the other nodes would just need to know about the QPs for the one that is broadcasting the data. Whereas if for an all-to-all connection establishment, you still need to communicate all of the QPs, as the name suggests, irrespective of the underlying communication. This is definitely not to demotivate the all-to-all connection establishment. It's just to say that how it is implemented and how it contrasts to the on-demand connection establishment, because it's necessary for most of the application. This kind of behavior is still there and it's still required as the current trend of applications putting a lot of stress on the network by doing these kinds of connections at application runtime. In general, this is a detailed comparison of the all-to-all on-demand connection establishment. As I just indicated, the all-to-all establishment should happen at the initialization time between all of the ranks participating in the communication world for MPI. Whereas for on-demand, it just happens during the communication phase or the communication setup preceding the underlying communication construct. So in terms of the number of QPs, we're looking at NP multiplied by NP minus 1, where NP indicates the number of MPI ranks. But for the on-demand, it's upper bounded by that number, so it's not always equal to that. It depends on the requirements for the communication. And if this obviously blows up the MPI init time for the all-to-all established connection establishment. So any reduction in this time would result in reduced MPI init time. However, for the on-demand, the happens during the communication, the MPI init time is not impacted by that. Yeah, in terms of the communication latency for the iterations, assuming that we have an iterative execution where you would call the collective iteratively, like let's say for the applications coming from the umbrella of the deep learning training, the OREDUCE collective would be called in iterative fashion. So for the initial iterations, they are actually, in terms of latency, they are consistent with the subsequent iterations. However, with on-demand, since you need to do this step that hasn't been done before at any time, the initial iterations are much slower. And definitely, the all-to-all is suitable for more complex patterns than those of the on-demand. Another motivator for this work is the current trend of HPC jobs, not just the HPC architectures. The HPC jobs are running on 8 nodes or smaller scale. So if we look at these excerpts from figures from the Exceed project, which is now Access project funded by NSF, on this figure here, we see that the majority of compute hours are spent in small node jobs. So the higher the bar is, means higher CPU hours spent in a job. So we see that there is a trend of increasing time spent in the smaller jobs. And also in terms of the number of jobs, just the absolute number of jobs, there are actually smaller jobs, and there is a trend of increasing in how many smaller jobs are being dispatched to the queues. So that's going from 2020 to 2022, and I bet the trend will be increasing until now. So in terms of actual time spent doing these kinds of operation, we profiled this on TAC Frontera system to see how much time is being spent doing the all-to-all RDMA connection setup with 16 nodes and 56 processes per node. And the data exchange of these identifiers of QPs constituted more than 80% of the initialization time. So this is a significant amount of time. Any decrease in this time is a significant contribution to the overall reduction in the latency. So the challenges are to minimize the data that is to be communicated during this QP data exchange. And to attack this challenge, we have presented a design to reduce the data being exchanged by doing this rank-to-rank, all-to-all connection establishment in a more efficient fashion and reducing the data to be exchanged, as I will show next. And another challenge would be to how to utilize the system characteristics to balance the overhead during this actual connection establishment. So we have, as I mentioned at the beginning, we had nodes featuring so many cores. So how can we utilize these cores in an efficient fashion to help us even with the connection establishment itself? And the last but not least, how to select the best connection establishment approach to benefit the overall HPC application performance. So we do a comprehensive performance analysis. I will show a few of these analyses in the talk, but you're welcome to look at the paper for more details. So these we can see from the analysis, this is like it's a case by case kind of scenario when it comes to applications, and more thorough study needs to be done on the benefits to applications. So moving on to the design and optimization section of my talk. So the first design is actually sparked by the fact that the vast majority of created QPs that are returned by the adapter, we have observed that these QPs are returned in ordered in their IDs. So they are returned in order. And there's very small chance that the QPs are out of order. So we leverage this observation to come up with a design to reduce the amount of data being transferred by the QP IDs. So here is a figure showing how we call the IBV create QPs, which is an IB verbs call. So this function will return the QP per each rank, and these QPs, if you look at this figure on the side, it shows that these QPs are actually in order, in numerical order of their IDs. So we're looking at 1, 2, 3, and then there is a disconnection, and then 5, 7. So they are in increasing order. We don't see any QP that is coming out of order. That's based on observation of the vast majority of the QPs being returned by InfiniBand RCAs. So in order to leverage this observation to come up with a more optimized scheme for exchanging this information, we are pushing these QPs in ranges. So imagine if you had a fat node of many cores, how much reduction that would constitute. So this is a very small example with just 6 QPs. So that would end up as, for these QPs that start at 1 and with 3, we have a range of 1 to 3, 5 to 5, since there is that's the only one in sequence, and we have 7 and 8. These are retrieved and they are pushed to the target rank in the exchange process. So here's an example of how the PMI or the process management interface exchange process takes place. First of all, we communicate as a static information, that is the architecture and HCA network adapter. So it's this kind of information is 1 per node. However, for the individual IDs, for the QPs, for the underlying ranks, each of the ranks need to send its QPs, so that the optimization mostly happens in this part, where, as opposed to the previous conventional scheme, the individual numbers are communicated. However, now we're sending ranges instead of individual IDs. Another observation is that the QP creation initialization is a major overhead for MPI init, initialization time for MPI. And this process is potentially and inherently parallelizable. So if we look at the figure on the right, we see that the IBV create and modify QPs constituting at least 60%, going from 2 nodes all the way to 16 nodes with full subscription. So in order for us to reduce this time, we have used OpenMP to parallelize this particular part of the QP creation. So we query the HCA in a parallel fashion with multiple threads. However, since we are dealing with MPI and it's not a clear cut how many threads can be used per MPI process to do these things in parallel. This is a tuning problem, how many threads to use in that in order to create the QPs. So based on our profiles and on this particular setup, we adopted a greedy approach to see what is the optimal or the sweet spot where we get the best performance and lowest latency for the QP creation initialization, and we're getting around 8 threads on the tag frontera in the epic nodes. And this particular portion of the code is done before before the MPI affinity configuration, because it will interfere and cause some performance degradation due to the CPU binning. So we made sure that it is done in the appropriate place so that it doesn't incur any degradation on the MPI affinity setup that needs to happen due to setting the binding policy at the MPI level. So to evaluate the performance of these enhancements, we are using MVAPitch 237 MPI library in conjunction with the OSU micro benchmark with version 5.9, and the applications, or I'll say the HPC benchmarks that we have used are the NASPERL benchmark with version 3.4.2 and 3D Stencil benchmark. And the experiments were conducted in two systems. The first system is the TAC Frontera system at the Texas Advanced Computing Center and the Lone Star 6. Frontera features Intel Cascade nodes, whereas the Lone Star system features AMD EPYC nodes. And we're looking at 56 cores per node in the case of Frontera, and 128 cores per node looking at Lone Star 6, and both of them communicate over IB network on 100 gig and 200 gig network respectively. To start off, we profile the startup time, the initialization time, and in these figures, lower is better, of course, and this is latency. And we're comparing with the default all-to-all initialization time versus the optimized one. And we're also, for completion, adding the on-demand establishment for connection establishment given its initialization time. However, it's not really an apple-to-apple comparison because there is not much there's not at all connection establishment happening with an MPI in it for on-demand, but we included that for completion. So we see that there is a significant improvement with the optimized design. It's almost matching the on-demand connection establishment in the high scale that we've tested on with Frontera. And that is the 16 nodes with 56 ppn. And here we're measuring the all-to-all, OSU all-to-all latency. And also for when we do the broadcast operation, we are also seeing noticeable benefits comparing the red bar to the blue bar on both Frontera and Lone Star. And as I mentioned, the first iteration latency can make a difference because for on-demand, it takes more time as you're doing that connection establishment just before the communication. So with the all-to-all startup design, we're getting up to 400x faster execution time of the all-to-all, and as well as for the broadcast, we're seeing noticeable benefits. And here we're also showing just the first iterations, as opposed to what we showed previously of the average of all iterations. And you can notice the dramatic differences between on-demand and the optimized all-to-all connection establishment, given the all-to-all benchmark. We did some HPC benchmarking. So for the 3D stencil communication, we get up to 10 times faster time or faster execution time for the optimized all-to-all connection establishment compared to the existing all-to-all startup design. And we see the relative differences in this figure over here, with the total execution time being improved, as well as the communication latency, with the exception of the few cases anomalies that we see at a larger scale for 3D stencil. And as I said, it's not really straightforward at the application level. However, what we're seeing is an actual and tangible improvement for that particular phase for connection establishment. And there are applications where there will be definitely benefits, and we're waiting for your applications to run MVAP pitch and experiment with these designs to see how these are benefiting the more convoluted kind of applications. For the Fourier transform benchmark, the total execution time, of course, it is better than the default all-to-all due to the enhancement that we constituted on top of the baseline design. However, the throughput is higher even than on demand, because that benchmark also outputs the throughput. So for the throughput metric, it's actually 31% higher compared to the on-demand startup approach. So in conclusion, I know I'm finishing up a little bit early, but we can take some questions depending on the time. So in conclusion, we have been talking about the connection establishment methodology and how it became crucial for the overall performance of HPC and DL jobs. We've also investigated the bottlenecks for existing state-of-the-art all-to-all connection designs and proposed a new design for enhancing the rank-by-rank connection establishment. All of these designs are part of the MVAP-2 library. We just judging from the MPI init time, that is a straight to 20x reduction in the latency of MPI init. Only at the micro benchmark level, it's reproducible and noticeable benefits for MPI init time. And that's also a 31% higher throughput with the NAS Fourier transform HPC benchmark. These designs are not yet available in the present releases, but they will be made available in the upcoming MVAP releases. So stay tuned for these. We will announce them in time. And we plan to extend the design to support additional architectures such as ARM and more network adapters such as the Broadcom-Rocky that I covered. And actually, we're testing that design on Broadcom-Rocky nowadays, and as well as PSM. And with that, I would conclude my talk, and I'm happy to take any questions.
Great.
So, okay, I have one question. So basically for this all-to-all communication, oftentimes you don't need all the all-to-all connection. Have you measured how many of the part of those connections are actually used by the application or by the benchmark in your test?
So can you repeat the question? Are you saying that for some portion of the applications, we don't need all of the QPs?
For example, if we're doing an all-to-all collective, I mean, usually the best algorithm is not doing exactly all-to-all.
That's right.
Yeah, communicate. Yeah, you're going to do some kind of hierarchy, log
yes, that's right.
level. Yeah. So basically, some of the connection you established is maybe not being used at all.
That's right. Yes.
Have you have any measurement in the actual example how much of the connections are being used?
I think we don't have that in this talk, in this part of the work, but I think I get your question. So we support a variety of all-to-all algorithms, including those that don't require establishing connections on a rank-by-rank basis. That's even like one of the results that I'm showing could be using some of these algorithms, but I don't know what the exact algorithm on the top of my head, because it's a tunable. It's a tunable parameter as I presented yesterday. So I'm pretty sure that this is a scenario that we've tested, but we haven't identified the link between how many QPs are required versus how many we're establishing. However, these enhancements are especially there for the connection setup phase, irrespective of what is coming in the communication footprint of the application. So if you had that in the beginning, and I think it can be required at some point in the lifetime of the application that you would need to establish a connection anyway. So that's just optimizing that particular phase, but it doesn't suggest that the algorithm or the way you're conducting the connection need to actually abide by the all-to-all pattern. It doesn't suggest that.
Yes, I mean that is because my point is basically sometimes the on-demand connection setup strategy could be lighter on the resource requirement, and when the scale comes to be very larger, trying to establish the all-to-all at the beginning could potentially, make the resource be very, sometimes you just cannot reach that scale.
That's right. That's right. That maybe there is something that I didn't highlight well in the talk, which is that these designs pertain to the RC connection establishment, where you usually communicate at a smaller scale, and it has already the requirement of doing these NP squared or rank by rank connection establishment as for RC based or RC class of communication, which you usually do at a smaller scale, but definitely at a larger scale, much larger scale, on-demand establishment would be more efficient. But where RC has a lower latency, then it's inevitable to establish the connection this way. Therefore, any benefit that you constitute by incorporating designs to optimize the all-to-all style of connection establishment will benefit these RC class of communications that happen at a smaller scale.
I have a second question. Have you ever looked into some kind of comparison between this out-of-band connection setup and using RDMA-CM?
I don't think so. Doing RDMA-CM versus this
out-of-band exchange information and modify QPL directly. Any kind of comparison between these two in your experience?
No, I don't have, but we will look into that definitely. I don't have that comparison.
But that's fine. Okay.
Thank you.
Cool. Thank you. Arlen asks, with CPU core counts continuing to increase, at what point does it make more sense to offload compute with OpenMP similar to GPU support?
So the references that I made to OpenMP in the talk just pertain to the QP creation part, but I'm not suggesting that any part of the computation should be done on the CPU side. It's just like when you have a system that let's say features a node with many cores and also has accelerators, and you would like to interface this node to the rest of the nodes of the system, you would still need to do the establishment for the CPU cores. And I think offloading the part of the connection establishment to the GPU cores would not really have much benefit because it's already happening on the CPU, and it's not that much of a costly compute-bound process. But perhaps like for the advent of GPUs that already have interfaces to the NIC, these designs can be incorporated.
Cool, thank you. Do we have any final questions for Mustafa? Okay, thank you very much, Mustafa. I appreciate your talk.
Thank you so much. Thanks for the questions.